Hi, today we're going to go over the power design of a matrix-compatible automotive LED headlight with multiple dynamic features that require pixel-level control of the headlamp LEDs, such as sequential turn signals and adaptive front lighting. Keep watching for a demo of this reference design that we control with an easy-to-use GUI, or you can view our fully tested design files for this small, thermally efficient design by going to ti.com or clicking on the link below. Implementing multiple dynamic features in an LED headlamp requires the headlight electronic control unit, or ECU, to have a two-stage power architecture, as seen in this block level diagram. The flexible TPS92682-Q1 LED controller is configured as an interleaved two-phase boost converter and is used to boost the variable input voltage from a car battery, which ranges from 6 volts to 24 volts, to a steady DC voltage of 50 volts. This steady voltage output is then fed into two TPS92520s, which are dual synchronous buck LED drivers capable of running from 400 kHz up to 2 MHz switching frequencies. These LED drivers provide 4 constant current outputs of up to 1.6 amps per channel to power the headlamp LEDs. The buck power stage allows the use of a small output capacitor, which is essential for pixel control applications due to the frequent shunting of the LED string as individual LEDs are turned on or off. Both the TPS92682 and the TPS92520 share a common SPI communications bus, which is used to program output set points, set control characteristics, handle faults, set limp home mode behavior, set switching frequencies in the buck, and spectrum properties in the boost. This design also includes a full mechanical metal enclosure to improve the thermal performance of the design. The TPS92520 is a synchronous, so the low-side diode, which is the largest and hottest component in a typical ECU power design, is eliminated. It also has a top thermal pad package, which allows direct thermocoupling of the buck IC to the enclosure, which typically doubles as the heatsink for the ECU module. This improves the overall system thermal performance since the power dissipation does not have to travel through the PCB and allows the module to run much cooler than conventional designs.
We have two TPS92520s that drive 4 LED channels to obtain 30 watts of power to each channel for a total of 120 watts. Each TPS92520's temperature rise is only 10 degrees, even at the full power of 60 watts per device, or a total of 120 watts. The rest of the module runs with relatively small rises of temperature due to the efficient thermal design of the system. This design demonstrates that a small solution size of 3.61 inches by 4.28 inches can be achieved for a 120 watt ECU. This small size, when combined with a high efficiency on the order of 89% at full power, allows for high power density and good thermal performance without the need of a large and expensive heatsink.
Next, we will give a brief demonstration during which you can see the complete headlamp system in operation, which animates LED features implemented smoothly via the Matrix Manager IC.
Here, the TIDA050030 is hooked up to an LED load board with our TPS92663 and 662-Q1 LED Matrix Managers. We are controlling the demo via the CAN interface using a GUI that leverages the industry standard software tool Vector CANoe. Now we will demonstrate multiple headlight functions, starting with the daytime running lights. Here's the first daytime running light being turned on and turned off. Here's the second daytime running light being turned on and off. Next, I will turn on the high beam and the low beam. Low beam, high beam, low beam, then off. And here's a sequential turn signal. The LED matrix creates a precise, smooth animation, and the buck continues to regulate unaffected by the dynamic load. The boost in front of the buck creates a stable rail that is always ready to provide a high enough voltage regardless of the LED string length due to the matrix. Finally, we have real-time pixel level control of each headlamp LED, which is needed for adaptive headlight functions, which automatically adjust the intensity of light emitted from the headlamp based off real-time inputs from the vehicle's front-facing camera. Examples of adaptive headlight functions include cornering lights illuminating the road based on the steering angle, detecting and illuminating road obstructions, and creating anti-glare zones to prevent blinding oncoming traffic. As you can see, we are able to individually turn on and off each LED as needed through the shunt vent dimming. In this demonstration, we are changing which LED is being bypassed using the moving slide on the GUI to represent the desired LED to be shunted by the FET. Additionally, we can individually dim each LED using PWM dimming. Each individual pixel is dimmed with varying levels of PWM dimming to create a gradual light transition from pixel to pixel, creating a lighting gradient.
As you can see through the demo, the two-stage boost anti-buck ECU is able to control LED current accurately throughout the load transitions during animated LED headlamp functions. By downloading our test design files, you can easily copy and paste your way to a small, efficient power design for your headlight ECU. Go to ti.com to get started, or click on the link below.